Example time. Let's do an example with nozzles and diffusers just to show you how they work. This is essentially just an application of the energy balance equation we already talked about, but we'll go over how to apply it with a nozzle in this case. So for this problem, we've got air. It's got a mass flow of 2.3 kilograms per second, entering a horizontal nozzle that's operating at steady state at a temperature of 450 kelvins and a pressure of 350 kilopascal. We've got a velocity of 3 meters per second. At the exit, our temperature is going to be 300 kelvins and the velocity will be 460 meters per second. So notice, sped it up quite a bit. Using the ideal gas model for air with the constant specific heat, constant pressure of 1.011, we want to find the inlet area and the heat transfer between the nozzle and the surroundings in kilowatt. Okay, that's what we're looking for. Keywords first. We've got steady state. Definitely want to pay attention to that. And we also have the ideal gas model. So those are our two keywords that we really need to pay attention here. And we've also got these values, obviously, that we will need. Now I'm going to go ahead and draw a picture. So there's my nozzle. I've got air coming in here. Temperature is 450 Kelvin. Pressure is 350 kilopascal. Speed is 3 meters per second. At the exit, I've got a temperature of 300 Kelvin and speed is 460 meters per second. Now, we were given the mass flow also, right? We had 2.3 kilograms per second. That's going to be m dot. And notice this is steady state, so this mass flow rate goes for the inlet as well as the exit. So there's only that one that we need. All right, so now I got that. Now, to get started, let's see, what do we want to do first? First, remember, we're going to have an ideal gas model. So let's write out our equations we're going to have available to us first. We've got an ideal gas model. So remember, that's pressure equals rho RT. We also have this m dot. We know m dot is equal to rho AV, which is also equal to AV over V. So that's what we have to look for. We want area, right? Area is what we want. So we need to find a way to find area. Now this has area in it. So if we can use m dot, we can find our area. So let's figure out how to go about doing that. Velocity at the inlet, we know that. We know m dot. So if we can find density, then we can find area. So density is our next step. So we'll put get density. And to get density, how do you think we should do that? If you look to this equation over here, we've got density, right? So let's solve this equation for density, and then we can plug that value into this equation for m dot. Then we will be on our way to solving for area. Rho is going to be pressure over R times T. Pressure at the inlet is 350 kilopascal. Let's convert over like we always do. So 1,000 Pascal per kilopascal. Multiply that by 1 Newton per square meter over 1 Pascal. This gets everything in terms of newtons and meters. In the denominator, we need R. Remember, R is R bar over molecular weight. So you get 8.314. That's kilojoules per kilomole Kelvin. Put that over molecular weight for air, which is 2897. That's kilograms per kilomole. Now that gets rid of moles. Now we are left with kilojoules per kilogram Kelvin. Let's get rid of the kilojoules. We don't want kilojoules in there. So let's convert over to joules first, and then from joules to Newton meters. So there's 1 Newton meter per joule. This takes care of all of that. And now we need temperature. So our temperature is 450 Kelvin. So now we have that. This K cancels out with that one. Now if you look at your units, you've got Newton per square meter up here, you've got Newton meter here. All right, so now what you're left with when you work everything out is 2.71 kilograms per cubic meter. And you're probably wondering, where is this kilograms from? Remember, newtons has kilograms in it. So 1 Newton is 1 kilogram meter per second squared. All right, so I'll let you guys look through the units, see how you get that, if you're not seeing it right now. Okay, but now we've got density. So this is our density at the inlet. So we're going to plug this number into this m dot equation. Right, so we've got that. And remember, this is row 1. So we're going to have 2.3 kilograms per second. That's got to equal 2.71 kilograms per cubic meter times the area times the velocity, which is 3 meters per second. All right, now if you look at your units, kilograms go away, seconds go away, you're going to be left with meters squared. Solve this for A1, you get 0.2829 square meters. So that's your initial area. All right. And then for part B, we want the heat transfer between the nozzle and the surroundings. So that means we want to find Q dot. Now for this, you're going to use your energy balance equation. Anytime you're wanting to find Q, we always use that energy balance equation. So I'm going to write out the full equation, the steady state version. So we've got 0, it's going to equal QCV dot minus WCV dot plus M dot times H1 minus H2 plus 1/2 V1 squared minus V2 squared plus G times Z1 minus Z2. So this is the full equation. I gave you the simplified equation in the last video, but if you don't remember the simplified equation, you can always just start with this main one. Elevation we don't care about. That can go away. W dot, we don't have any other sort of work other than flow work, so this term goes away. This is what we are looking for. So if we can find the H's here, then we'll be good to go. Because we already have the speeds, we already found M dot. So we have everything else, we just need to worry about these H's. Now, consider the fact that the problem gave us the CP value, specific heat at constant pressure. That was given to us, right? So remember that we talked about how H could be CP times T, right? So CP times the temperature at the inlet is going to give us H1. Same thing here. We'll have CP times T2. So these are 2 other equations you can use for H. If you're given the specific heat value, you don't have to go to the table and find the H values. You can just use this expression here. All right. In this problem, because we do have an ideal gas. Now, with that, let's go ahead and plug in our numbers. So we got 0 equals QCV dot plus M dot, which is 2.3, Now we're going to multiply that. I'm going to pull this CP out, and I'm going to convert it over to joules per kilogram Kelvin. It was given in kilojoules, so let's convert it over to joules. So that'll be 1011 joules per kilogram Kelvin. Multiply by the temperatures. So 450 minus 300. Then we're going to have plus 1/2 times 3 meters per second squared. 3 meters per second, square that quantity. That's what I meant to say. Minus 460 meters per second, square that quantity. Now we're left with this. All right. So now that we have that, let's go ahead and go a step further. Now we're going to have 0 equals QCV dot plus 2.3 kilograms per second, and then let's take care of all these calculations here. This is going to give you 45,854.5, and the units now, if you look at the units, break this down, this is joules, you're going to get meters squared per second squared. Now remember, 1 joule is 1 Newton meter. All right, so if you're looking at the units, keep this in mind. And we already said that a Newton is 1 kilogram meter per second squared. All right, so that'll help you figure out how we got meters squared over second squared. Now that we've got this, let's go ahead and keep going. Let's solve for Q dot. Q dot is going to be negative 105,465.35. That's kilogram meters squared per second squared. We want the units of Q dot to be in kilowatts. So let's figure out how to do that here. Remember that 1 watt is 1 joule per second. And if a joule is a Newton meter, then that means this is 1 Newton meter per second. Now look at what we've got here. If we've got a Newton meter per second, that means we're going to have kilogram meter per second times meter per second. All right. Whoops, I'm forgetting one here. That's squared. So the Newton is kilogram meter per second squared. So now if you look, you got kilogram meter squared per second cubed. That's exactly what we have here. All right, that's a watt. We want it in kilowatts. So to go from watts to kilowatts, we just need to divide by 1,000. All right? So that's what we'll do. So QCV dot then, once you divide this by 1,000, will be negative 105.465 kilowatts. Okay? So that's how you go about doing that. Now pay attention to this sign here. It's negative. So what does that tell us? Since it's negative, we've got heat transfer from the air to the surroundings. All right. Hopefully that gave you a good example on nozzles and diffusers. Remember, the main takeaway for nozzles and diffusers is that you can change your speed and your pressure just by changing the area through which your flow goes. Okay. Now I will see y'all in the next video where we'll talk about turbines.